Yo, yo, yo. What's up? What's up? Welcome back. Today we're working on my custom operating system for x86, written in Rust. And the goal for today is to start working with like TCP retransmission. So what we have right now is we have this operating system. It boots. It has like memory allocation. It has async support. It has like serial output, VGA output, unit testing, some drivers for like RTC, PCI, Ethernet, etc. And then like we've started building like the network layer recently. So we're kind of working on like trying to like resolve IPs with ARP, send UDP packets, receive UDP, send TCP, receive TCP. And where we got to last stream is we have this like TCP echo server that's working as far as we can tell. So here, if I open up Netcat and I start typing stuff, we see it like pop up a second time, which is an indication that our operating system is like receiving that packet and sending it back to us. So what we have working right now is like not correct, but it's correct enough that we are sending and receiving packets, which is pretty cool. So there's some things that I want to fix here, and specifically like our TCP implementation on our operating system that we got to do last time is like not reliable at all, right? If we send a packet and they drop it, we're just like, what? Okay, if you say so. And like if there's any drop packets, like the whole stream will just fail because the client that's talking to our OS is going to just start acking with like the wrong packet. Is going to be like, oh, I don't have this one yet, and we don't handle that at all. So that's what I want to look at. Yeah, let's get into that. So I guess before that though, I made some like off-screen fixes. So if you've been watching or watched a previous episode, there were some things that we got to that we like kind of gave up on, and I took a second run at it off screen. And just wanted to quickly take a quick look at that. So the big thing was that we had this like polling loop where we were every n seconds or like every 30 milliseconds, we were polling our TCP service to see if there's like anything to write to the output. And that worked. But like the downside of that approach is that we were waking up our executor too often, which causes like overpolling, extra CPU usage, etc., etc. And we got almost there last time. We got to the point where we had like written this feature that like checks all of our TCP states, and it checks if there's any that are connected, and it then like waits for us to try to send data and converts that. And that was working. Sorry. Ooh, that was working okay. But what wasn't working was if there were no connected sockets, we were getting stuck. And all we had to do was add this second feature that says like, wait for there to be any connected sockets, and then this second feature will work okay. And that was pretty easy to implement. All that is we like iterate over the TCP states. If any of them are connected, we say that we're ready, and if they aren't, then they're not. And that was working pretty good. And in the process of implementing this, I also noticed that that we were waking up our executor really frequently because of the logger. The logger was doing the same thing, where here previously he was saying like, I'm going to sleep for 60 milliseconds every time there's no more logs to print, and then I'll try again. And we can just do the same thing actually that we did there, where we create a log waiter feature that just polls to see if there are any logs available, and then our loop becomes like a lot cleaner. And so now, if I like look at our current OS, we can look at the future executor, which will be in future. And if in here I just print every time we try to poll, what we should see is a very infrequent poll, right? We poll when we start seeing data come in, We poll when a log is written, but otherwise we're actually like most of the time sitting pretty idle, which is sick. Right? Like before we would have seen this like spam. Hey yo, what's up? So pretty happy with that, and we're in a pretty good spot to just start trying to like work with TCP retransmission. So let's get into that. So there's a few sources that I've been reading to try to figure out what I'm supposed to do there. Let's pop up in the browser. So one is I've been looking at the TCP spec from the IETF, and there's actually like a lot of technical detail in here, but I actually found this like kind of hard. Like found it kind of hard to deal with finding what I'm supposed to do. It seems like it's pretty thorough, but I actually couldn't find things like I've read in some places that if you receive 3 ACKs in a row, you're supposed to retransmit a packet. Stuff like this, like people talk about triple ACKs, and on Wikipedia there's all sorts of things that they talk about. They talk about like timeouts, they talk about triple ACKs. And I found that like hard to find in the actual protocol definition. So like here they talk about like dupe ACK based retransmission, etc. So I think that what I'm going to do is I'm going to try kind of like to piece together the information that I can and try to figure out if I can like implement something. And maybe what we'll do is we'll maybe try like dropping some packets and observing what the Linux side is doing, right? Because we have like our ROS, but we're running our OS from a Linux host, and he's sending stuff to us. And so what we can do is we can like drop some packets and see what happens when he does that, which is pretty good. So I think that we'll just start there, and we'll start by like observing how we fail, and then try to patch over those problems and continue on. Which means the first thing we have to do is actually implement some sort of way to like randomly drop packets. And we actually have no concept of a random number generator right now. So if we want to like drop 1 in n packets, like how the fuck do we do that? And so the first thing that we actually have to do is like implement a random number generator. So I think that this is like a pretty complex topic just generally, but I think that we kind of already have a piece of something to give us something good enough, right? We don't need perfection here. We don't need a perfect uniform distribution or Gaussian distribution or whatever you want to say. We just need something that looks like approximately random, and that if we were like, I want to drop 10% of packets, that we get like approximately 10% of packets dropped or something. And I think what we can probably do there is we can start with just using our hash implementation for our hash map from Hashbrown, and just chopping that up and seeing like, yeah, we can maybe just hash a number that's incrementing, right? We increment by 1 and we hash that, and that's our random number. And then we remapped that to the range that we care about, maybe. So I wanted to like look at that and see if the distribution from that is good, and if it is, then we're good to go for now, right? And we can just like seed it with like the RTC time when we boot or something, which is not secure, right? A big problem here is that a lot of the complexity from RNGs, I think, comes from like trying to be truly random and use like entropy from the OS and stuff. I don't care about that right now. I just want like something that appears random to me. So let's start there. So I think that if I remember correctly, there's like a hash implementation in the Rust standard library. And I'm not sure if that's what we're using, or we're using something that's provided by Hashbrown itself. There's this like default hasher, I think. Or maybe hasher. Yeah, so we have core hash sip hasher, which is a general purpose hashing function. It runs at good speed and permits strong keyed hashing. This lets your hash tables from a strong RNG. This lets you key your hash tables from a strong RNG. Okay. So, but this is deprecated because they want us to use default hasher instead, which doesn't look like it's in core. But they do just map the default hasher to sip hasher 13, which I actually don't know if we have access to. Right? If we look at sip hasher, is this So yeah, this is SIP hasher 24, which is like a different thing. I don't know how it's different. Probably version. Here we go. Yeah. Okay, interesting. And then let's look at what we're using right now when we use our hash maps. So here, hash map here. This guy is using some default hasher that is actually from a hash. So what is a hasher? So high performance keyed hash function, high quality hash where the result is not predictable without knowing the key, but without allowing for the possibility of a malicious user to induce a collision. Okay, so it's using AES and it says it's fast. So maybe we just use that for now because we could use like the SIP hasher given to us by the standard library, but they're like explicitly telling us not to, and we could maybe like get around that by using some internal thing with core and nightly, but it seems like it's just easier to use the hasher we already have and that we're already using. So let's take a look at that. So probably, I think we say that we're gonna like make like an RNG. We're gonna call it random number generator. And you have to include it, so maybe this should be in util, right? You could argue that this is like a utility, or you could argue that this is like a core part of the kernel or something. So I'll just leave it at the top level for now. We'll just name it random number generator, and we need to make it public so it's usable, and we need to make it constructible from the external world. So we'll say pub function new returns on RNG. Ring. Okay. Which means that now our kernel on construction can make an RNG. Right? So we'll add it to like the state of our kernel in general. And drop it in here, and we'll just say let RNG is RNG new. Which means we have to use RNG, blah, blah, blah. Which comes from our crate, so RNG. Can I suggest something like XXH3? Let's take a look. What is this? Extremely fast hash algorithm, processing RAM speed limits, blah, blah, blah. So it looks like it's just speed focused, probably similar. Okay, so I think it would be worth exploring. But I think one of my goals in general is to try to like avoid pulling in dependencies that I don't need. So I think that I'm okay with using the a hash that I already have, and arguably I shouldn't even be doing that. Arguably using hash brown is kind of cheating, right? I kind of like in my head I want to be able to say at some point that I wrote all the code, which, it's not really, using the standard library makes it kind of arguable that I it's not true, but, pulling in dependencies just cause, I'd like to avoid at the very least. So I think for now, I'm just going to at least try to limit it so that later it's easier to deal with. So I guess this guy is going to have his hasher in here that comes from our hash brown thing. And somewhere they construct this guy, which is build hasher default a hasher that probably has some way of like constructing the hasher from this. So let's just see what this looks like. Where we say let hash builder is this guy. Maybe I put a new in here. How do I use this build hasher default? Let's see. Probably I can just use hash map default hash builder actually. So we have let hash builder is hash brown hash map default hash builder, like this. And can we like make a new out of it? Let's see what the default hash builder API is like. Oops, this was build hasher default is the actual word for it. Build hasher default. And presumably I get a hasher by typing build hasher. Cool. So say let hasher is hash builder dot build hasher. And I guess the problem here is that we actually need to be able to construct these guys. So how do we do that? What does he do here? He says default hash builder uses this. And can I like construct him? Pub enum default hash builder. Dummy default hasher for hash map. Oh, because if we don't have a hash on. Okay, sure. How does he construct him? He calls make hasher, which is something that he can only do internally. Oh, maybe this becomes like a little bit of a pain if I don't pull in a hash directly. How do these like hash builders work? With hasher in. Oh, he just calls : default. That seems useful. Ah, very nice. Very nice. So now I'm missing the build hasher function. So what's this guy supposed to have? Am I missing something? In this core hash build hasher default, which is I think what this guy is, we're supposed to be able to call function build hasher. Hash builder. Let's just see what the language server says that I have on here. It's kind of giving me like no APIs. Oh, it does say that I have this if I call build hasher. So why doesn't he like that? Compiler's still complaining. Oh, because I don't have the trait in. Use core hash build hasher. Aha. There we go. Okay, so now I have a hasher. I don't know if this has like state associated with it. I guess it doesn't matter. And I guess I'll just put this guy in here. So we'll say that this is a hasher, which I don't know if I actually have that type available because it's like nested a crate in. That's kind of annoying. Maybe I actually do have to pull in a hash directly. Let's just see real quick. A hasher. Yeah, that's kind of annoying. I guess probably a hasher implements something, and maybe I can like avoid this by doing some like generic type finagling. So I'll look up a hash real quick. Oopsies, that's not docs. A hash on docs rs. And he probably implements hasher or something. Yeah, impl hasher. So we'll just say h, where h is a hasher. Okay, that works for me. Well, yeah, that's fine. That's fine. And we just need to do the same thing here, where we put an h in here. I think it's the colon goes here, and then this just passes in like this. Hasher. Oops, there we go. And this has to have the h as well. What doesn't it like now? Oh, probably in main. I have to like propagate this. Ugh, generic types are such a pain in my ass. So do I actually have to do the same thing here, where I have like an h here and an h here? Ugh, gross. Maybe it is worth it to just pull in the library directly so that I don't have to like pop this all over the place. But maybe that's it. If that's it, then it's like manageable. one more. So I'll just shove an H in here and an H in here. One constraint. If this is it, yeah, if that's it, then it's fine. Where was that? That was at line 567. Consider giving kernel an explicit type. So here I can say where H is core hasher. Cargo check. Unsatisfied trait bounds? Are you serious? Found struct a hasher. Okay, so this comes from RNG. H build hasher. Yeah, I think that this is not worth it. I'm just gonna pull in a hash, which is like not technically an extra dependency because I'm already using it. Oi, 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 oi. Okay, so let's get rid of all these like fucking generics. Go roast, get these guys out of here. We'll say this comes from a hasher. Now how do we make one of these guys? A hash map, no. What the fuck? Build hasher default a hasher. We'll just directly put these everywhere. Undo all of these generic adds in here. I think that was it. And so here, instead of calling this, we say core hash build hasher default a hasher default or something. And then here we use a hasher, and we pass in hasher here. Target check. Are we chilling? Target is not supported. Ugh. Is there like a feature? Oh, he has an SE feature, so we can just take that out probably. So we go to cargo, toml, we look at our dependency, we say our version is this, and the default features should be disabled. And we're close. We just forgot some double colons somewhere. Right here. All right, geez. That was rough. Okay. So, looks fine. Looks fine. Okay, so now how do we actually use this thing? How do we actually use this thing? So we can write in a value to it. How do we get the value out, though? Finish. Oh, I see. So we punch in, for our case, where we're just trying to get a random number, we can punch in a integer that we just increment every time and then finish it every time. I wonder if there's like significant overhead to that. But it doesn't matter because it's the only way to get the value out. Okay. So we'll say that our state is a U64. And our state is U64 is just 0 U64 for now. Now we will say that our function will say get random number. Is that, and maybe RNG, we just say RNG.U64. Is that a reasonable API name? I don't know, we'll see. This has to be by mutable reference because we're going to increment the state every time. And we're going to get a U64 out. And, okay, and then let's see, what do we want to do here? We want to say self.state plus equals 1 at the end. And then to get the value, it's just going to be self.hasher.finish. So then we need to inject the value. So self.hasher.write U64. Right? We stick that in there. We pull it out. We pull out the hash. and we should see something new. So it's bitching. I don't know why. Let's see, cargo check. It doesn't see that because we didn't use core hash hasher, the trait that has these like methods on it to actually do the work. And now we're chilling. Okay, so now what we want to know is like how random is this random number generator? And so I guess what we probably want to do is like make a histogram of the values and see what their distribution looks like. So let's put that here. So we'll say write a histogram. And how am I going to display this histogram? I will just probably put like, you can probably do something like this where you have like bar down here and you have like x-axis here, and you can probably just say like put some number signs or something to indicate height for each one. That's probably fine. We can visualize it and then we can just print it over and over again. That seems okay. You could also do like sideways and put them out like this. Okay, that seems reasonable. So let's start making a histogram, I guess. So we'll say that we'll just checkpoint this so that I have something to look at later. So this is at 2654-ish. And we're going to end this at some point. Bro, I came home from my coding job just to watch someone else code. Hey, I've been there. It's fun sometimes. You get like all this like satisfaction of watching problems get solved. That like, you know, you get that at work too, but there's something fun about it. I don't know. It's fun. Okay, so let's look at maybe adding a histogram. So we'll say like this seems like definitely a utility. And we'll say we'll just call it histogram. We have to include this in util mod, so we'll say pub mod histogram. Throw that in here. We have to make a class for it, so struct histogram. Is this going to be like a class? Does that make sense? Or does it make more sense to just put it, like have it be a free function that takes a bunch of numbers and buckets them? Yeah, we'll start with a free function and we'll upgrade to a class if we need it later. So no, you would need this to like render the data in some way. We want the data rendering to be separate, maybe. Fuck it. For now, we'll just say like pub function print histogram, and we'll take in some data of t's, right? I guess we don't really know what the t's are going to be at this point, but I guess we kind of need to know. So let's say that these have to be floats, right? We have a list of like continuous values, and we want to see how many are in each bucket. So we have the data, and maybe we need like a min and a max, or we can like extract those from the data, so that's fine. But we do want like a bucket size, but again, we can kind of like extract that from the data, assuming we know how many buckets we want. So we'll say we'll create a numBuckets variable, and this is just like usize, which seems fine. Okay, so what we want to do is we're going to take all this data, we're going to chunk it into these buckets. So I guess first we want to find the minimum and maximum value. Sorry, thinking. No, we don't need to do that. I think we just iterate over the data. We need the min and max. Well, we need the min and max to determine like what range this graph is going to cover. Then once we have the min and max, we can say that the buckets are of width max over, or like distance over n, and Yeah, that should be fine. That should be fine. So we'll say let min. There's probably some function to like iterate over a collection and get back the min and max in the Rust standard library, I bet. So there's probably like min max, max. Let's see what they have on like iterator, maybe. Let's see. Max by, min by. I guess they don't have a like get both. That's annoying. So if I want to get them both in one iteration, I just have to like do it myself. What a pain. What a pain. Ooh. I guess you could do like a reduce and your accumulator could be min max. But that's, I don't know if that's any better. Okay. So we'll make a function find min max from the data of F32s. And this returns min max. We have a struct min max, and he has a minimum and a maximum. In here, we're gonna say let min equals F32 max. And let max equals F32 min. I don't know if min is negative or not. Sure is. Okay, sweet. We iterate over all these guys, and for each value, we bump them if it's bigger. So we say for value in data, if value is less than min or is greater than max, max equals value, and if value is less than min, min equals value. What does he like? Stars here, probably. No. What's the type of value here? Value is an and F32. Max is a F32. So what does he not like here? Oh, maybe I have to dereference everywhere. Let value is star value. What a pain. And now we can return min max. So we'll say min max. Min max. Easy. And just for my own sanity, this is like very easily unit testable, and I'd be stupid not to. So we use our create testing star, I think, and use super star. We create a test that's called test min max, and we just say we put some shit into here, so we say like 0.1, negative 0.5, 0.5, 100, negative 100. And we say tests. I guess we pull out the min max. So we say let min max is equal to find min max on data. What doesn't it like here? We give me a semicolon. Okay, there we go. And then we test that the min max min is negative 100.0. We can't do test EQ. We have to do test EQ with like some form of well, I was going to say that we have to do some form of epsilon, except that because we're working with floats that we've punched in by hand, the value that we punch in by hand in both places should be the same. So this is actually okay. And these should pass. So cargo test, let's just double check. And we should see that the test min max is good. Yeah, so we're chilling. Okay. So let's get the min and max value. So we'll say let. I think you would actually do this like fun little destructuring where you say like let min max equals find min max on data. There we go. And then I can say that the let bucket width is going to be num buckets max minus min divided by min buckets. Is that right? As F32 These are already F32, so we just have to say num buckets as F32. And so if these are, if I have like 100 and 0, I'll do 100 over into 10 buckets. So I'll do 100 over 10 gives me 10. Yeah, that seems reasonable. And just for my own sanity, we're going to say calculate bucket width. And this takes in min, max, num buckets. And returns an F32. This is calculate bucket width, min, max, num buckets. And this just goes here. Which lets me just quickly bang out a quick little test. Test, calculate bucket width. What does he have? So we have test EQ, or I guess test true, because we need to do with epsilon because it's like math. We say that calculate bucket width. We'll say our min is like 0.1, our max is 0.5, and our bucket width is 0.1. Or our num buckets is, 4. We should see 0.5 minus 0.1, 0.4 over 4 is 0.1. That seems pretty reasonable. Let me like double check that by hand or by counting in my head. So we have 0.1 to 0.2, 0.2 to 0.3, 0.3 to 0.4, 0.4 to 0.5. Cool. So this absolute minus 0.1 should be near 0. So like 1e negative 9 or something. I think that's right. Is that how you do an epsilon comparison, right? So you say that like, no, this abs is wrong. This abs should be here. So we say calculate the bucket width, subtract 0.1 from it, which is like what we expect the answer to be. And if we absolute value that, it should be less than 1e negative 9. Okay, cool. They don't have an abs function on F32, really? I assume they did. Yeah, they do. Calculates the absolute value of self. So what don't they like? What the fuck? Is this primitive F32 should have an abs function? Am I crazy? Abs. Maybe I have to do like F32 abs on this. I don't see why I would. Why? Maybe this is implemented like only in standard library or something? Am I crazy? F32 abs 0.1. Very odd. Is this because like I need... That's very strange. I haven't seen this before. I guess I haven't tried to do this in... So this comes from... I guess this comes from... Ah, yeah. So this is in STD, not in core. That's interesting. So I probably just have to call this like intrinsics thing by myself. That's odd. I wonder why. Yeah, very, very strange. Okay. So where's this intrinsics thing come from? Core intrinsics. And then we have like fabs 32. Oh, and all of these are experimental. Fuck, man. That's so odd. So am I really just not allowed to like let's see. Core Rust abs F32. Let's see what the internet says. Here we go. So this is rustlang, and that's because these methods are in std. They're defined in libstd. No inherent methods. But why? This should be closed, go with this. And they want to not use libn intrinsics. Oh. Gross. So do I actually have to use, if I don't link libm, do I just not have abs? And do I need to just implement it myself? That's pretty funny, if that's true. Let's see if that's so intrinsics. Fabs. No, this should be fine. Okay. I guess I'll just use core intrinsics. I'll just enable the feature. Fuck it, I don't mind. I don't mind. Well, I mind a little bit, but not... If it's what I gotta do, it's what I gotta do. I don't want to have to, like, implement it myself. So this is core intrinsics. And here I have core intrinsics fabs 32. And here I pass in where to go? It's here. Let val is the this, and then I have unsafe core intrinsics fabs 32 val minus this is less than 29 cargo test. We're close. It's fabs f32, of course. Why would it be? And there we go. Okay. So if I run cargo test now, do we see success there? Boom, we do. Chillin'. Cool. Okay, so we have our bucket width. And now we just say for value in data, we check which bucket it's in. So I guess there's like fmod probably. Fmod f. It's probably in here somewhere. Fmod. No? How do I like floating point mod? I thought that there was an intrinsic for it, just like fmod f or something. Standard library fmod in libc. There's probably like divide with remainder. Is that what I want? I guess I can just do a divide and then figure out which bucket from there. So I say like, val over bucket width. And do I floor here? I probably floor. So we'll say bucket is the integer value of this division. So if I have like sorry, it can't be this just division because this has to be val minus min, actually. Let's think about that. So if I have a value of 0.2 in my test of 0.1 to 0.5, this will be 0.1 divided by the bucket width of 0.1, which will give me 0 or 1 depending on where it is in there, which sounds good. Then we can maybe make a map of these buckets. So we'll say histogram is a vector with zeros in the number of buckets. Right, so if we have like 10 buckets, we're gonna have 10 zeros. And then we should be able to say that our histogram bucket plus equals 1. And I think that that's it in order of like in regards with like implementation. And then we should just be able to say we want like a height probably to be put in here. So like height is going to be... No, we'll hard code for now. We'll say const height is going to be equal to the number of buckets times 0.75 or something, right? Like I'm trying to think, like we're gonna have a histogram where the number of buckets is gonna define how wide it is, and the height should just be something sane. So we'll just say that it's like if it's 10 characters wide, it'll be 7 characters tall. Fuck it. So we'll say times 4 times 3 divided by 4. Okay. And so now we can just start looping. So I guess first we need to find how many values are in each bucket, the maximum of all the values. That's going to be the max height. So we'll say let max count is equal to the histogram dot iter dot max. Right? Cool. Histogram, yeah, that seems reasonable. And then now we just say for bucket in histogram, we are going to print, let's think. Sorry. I'm actually going to make my histogram sideways because that's just easier for me to implement. So for each bucket, we're going to print line. First, we're going to print the number. The bucket number. And then we're going to print the character this however many times we need to. So this is just going to be count over max or something. So this should actually be bucket and count like this. This is going to be histogram.into iter.enumerate. We print the bucket and then a colon. And we probably need this to be like, you know, like a certain width. And then we'll just print this depending on the count. So we'll say for I in 0 to count over max count. Print this, maybe? Maybe? So what doesn't it like here? Cargo check. What doesn't it like? Cargo check. Hello. Integer over ops integer. Oh, okay. So we'll just expect no max value. Okay, try again. Okay. This needs to be copied out so that we don't have like lifetime issues. And there we go. Oh, this shouldn't be count over max. Oh yeah, that should be count over max count. This should be, this is the height in characters. This is the maximum number. And so this should be quantized to the height. So we can actually just multiply this by height. Yeah, there we go. Okay. So then we print line here. And maybe that's good to go. So let's try printing a histogram here just to see. So let's say here we're going to run util histogram print histogram of, you know, maybe some like floats. We'll say like 0.1, 0.2, 0.3, 0.4, 0.5. And let's say we have 5 buckets. And what we should see here is like a completely flat histogram. We probably need to put an ampersand here. And let's see what we get. Weirdly, we don't get anything because this is happening after the futures or after the whole OS runs. we have a problem here where the max value ends up being like slightly over. So we'll just say that the, right, so like if I have like 0.5 over 0.5, that's 1.0 times the length, and then we're like out of range. So we need to clamp this probably. Not clamp. So this is a bucket. The bucket should be clamped. So we'll say if bucket is greater than histogram.len, bucket equals histogram.len -1. And that should cover that like just slight issue there. So let's try cargo run again. It doesn't like this because it's not mutable. This clamp shouldn't exist, and I think we're chilling now. Nice. So we do get like flat here, which is great. And so now if I put in another 0.5 here, I should see the biggest bucket be bigger than all the others. Great. I'm a little concerned about the fact that these guys look like they're 0. That doesn't look right at all. So let's see here. So here our count over max count. So our max count should be like 2. Okay, right. So this is actually count times height over max count to avoid integer clamping problems. That's much better. Okay, cool. So we're seeing like if we have where our histogram now is being printed, like it looks like kind of sane. It's doing what we expect. And now what we can do is we can probably generate a bunch of random numbers. Right? Like let's make like 10,000 random numbers. We'll make this a vector. We'll store our values in this vector. And then here we'll just say v.push rng.u64. It does need to be self.rng u64 probably. Yeah. And then we'll print out a histogram for this guy, which is going to be v, like this. But we probably have to map these as a bunch to floats. So we'll say we'll get the u64. And we'll divide this by self.rng, or u64, sorry, max value as f32. And this is also as f32. Great. Close bracket. It doesn't like this extra brackets in here. And now we just need our number of buckets. So we'll say like 15 buckets or something. Okay. Nice. Nice. Okay, so we are getting like somewhat even distribution. So that's pretty cool. So let's say that this is finished at 5324 and this is also finished at 5324. I guess we don't actually know that it's what like the distribution looks like with a few. So maybe we can take a look at that. So instead of doing like 10,000, we'll do like 100. And that's a little more random, but that's okay. Maybe it's, and with like 10. Sure, that looks pretty random to me. Right, like we do 10, we get some doubles, we get some not. As we approach 1,000, or like as we approach a lot, we get somewhat even distribution. And I'm okay with that. That seems pretty reasonable to me. That is pretty sick. Okay. So now, I guess, what we have to do is figure out how to randomly drop outgoing packets. Incoming, outgoing. Which one makes more sense to me? Let's randomly drop our incoming packets, because then we should start seeing retransmission from our like Linux host as it's transmitting stuff to us. And then we can see if it's like doing retransmissions. Before that, I'm just going to hit the washroom really quick. So I'm just going to throw a quick BRB on the screen and be back in a minute. So text BRB. Okay, be back. And we're back. So this guy goes away. Perfect. Okay. So let's try randomly dropping some packets and seeing where that goes. So we'll say that we start this at around 52.4. That's great. Okay. How do we want to do this? Let's go to where we get incoming packets. We have this like handle packet, and probably all we have to do is here if say if RNG U64, or let's actually make our RNG have the ability to return float values between 0 and 1. We'll say normalized. This returns a floating point between 0 and 1. That just makes it easier to work with like probabilities in my head. So we'll say we get the U64, let val equals self.u64, and we'll return val as F32 over U64 max as F32. Easy. Okay. So now, our receive loop needs to take in an RNG. And in here we say if RNG dot normalized is less than, we'll do like 0.5, right? We'll just say drop packet. And we need this to be mutable. So we actually need a actually that's probably fine. We can just write mute here. If we needed to use this for multiple places, we'd start to be in trouble, but luckily we don't. So I think we can just do this. We can delete this histogram test we were doing, and we're almost there, 533. So here, we just need to move this stuff in, I guess. Oh, interesting. It's because this is an FN closure, not an FN mute. But I think that an FN mute should be fine. So I think that we can just say that this is, you're allowed to have mutable stuff in this function, and hopefully everything just works out. Cannot borrow on read, so I have to write mute here. Yeah, that seems like it's working. We can't drop the packet, but I guess we can just say handle packet. So we'll say we have a 50% probability of actually doing something. Cool. Oh, this needs to return an async block. So Yeah, that's fine. We just need to like throw some moves in a couple spots. Value of RNG moved into closure in previous iteration of the loop. So every time we call this read function, it generates a new future, which means that we can't actually move stuff in, but we could do maybe this. Does that work? No. Interesting. Let's see what it's complaining about. Jesus, lifetime bullshit. Returns an async block that contains a reference to a captured variable, which then escapes the closure body. That seems fine to me. Is it not? Ugh. Okay, so this just gets a little confusing. So let's just we'll do a mutex in here. Fuck it. And then probably all of this will start to work again. So we'll say lock dot await dot normalized. We go back here and we change this fn mute back to fn. So this is fn. This is fn. And we have this mute on read gets removed. I think that if I make this an async block again, this will work. Oh, weird. Still, eh? I thought that... So I wonder what the rules are here about, like, when I can... When I'm allowed to use this stuff or not. So is this allowed? Oh, interesting. So I just can't make an async block here. Okay. We're getting closer. So I guess we just pass in this stuff into handle packet and then it'll probably work. So here we go back to mutex RNG. We pass in the RNG here, and then for some reason that works probably. And then in here we say if rng.lock.await.normalize is less than 0.1, we return. This is a 50% probability of doing nothing. Now all of a sudden this works for some reason, but maybe because we're missing some, like we're not getting that far. So we'll make this a mutex protected RNG, which now probably needs to be correctly generated as a mutex. So let's say mutex new here. And I think we're chilling now. Cargo check. Okay, cargo run. So let's see what happens now. What we should see is if we netcat here. Nice. Okay, so we are seeing... Oh! We actually might be seeing reasonable behavior. So let's first log that we're dropping the packet, just so that we're certain. Which means in handle packet we say debug or info dropping packet. And we'll try running netcat here. That's a test. Okay. So we've dropped a lot of packets there. I think that our like renegotiation is like a bit of a problem. So let's just try a couple times here. We certainly are dropping a lot of packets. Okay. Okay, here we go. Yeah, okay. So we are in fact dropping packets. Which is a good sign, and we are in fact seeing issues with this. So we can start taking a look at this. So this is at 1:04:51, and now what we're going to work on is Handling dropped incoming packets. Okay. And let's see. Let's just start digging. So I guess we'll run this with dump network equal 1. Right? And we'll just say netcat hello. And that's working. Hello again. Hello again. Hello again. Test. Hi. Oh, maybe this is actually... Okay, so it looks like it's kind of like there are states that it will recover from. Yeah, that's interesting. So let's maybe take a look at the Wireshark capture from that and see if we can like gain any like interesting info from it. So here we have stream OS. We'll have this network dump. And what we should hope to see is a bunch of like TCP shenanigans. I don't like that this capture looks broken. Can we like look at this TCP stream? Follow TCP stream. So we sent a syn. It doesn't like checksums are incorrect, so let's just say that we're gonna disable the checksumming. Okay, so we try to talk to us. The first one doesn't get acked, so we try again. Maybe 1 second later. That one we ack okay. It doesn't like that our ether type it says is wrong. So why does it think that? Ether type. So that's going to be... What the fuck? The Ethernet type is IPv4. IPv4 type is TCP. So what is ether type here? Wireshark, malformed packet, ether type. Ether type, Wireshark. Yeah, I don't understand why it thinks it's wrong then. If I'm getting my Ethernet type of IPv4, how could it think that the ether type is wrong? All right, well, whatever. It's actually saying that every time we talk to actually everyone's saying that everywhere. So there's just some like mistake in here, or maybe there we go. So there was a problem where we were in Wireshark assuming that there was a checksum when it's stripped. So disabling that feature made this work. Okay, cool. So now we've got a bunch of purple. Purple makes it feel better. Okay, so what happens? The Linux host tries to send us in. It doesn't get through, so it sends it again. We ack it. It sends hello, which we ack twice. Why? Did we get them both? We should... No, this is one push. We ack it twice for some reason. That's weird. Maybe one of these is in response to syn-ack. Okay, that's a bug. Probably. Oh, that's because we're acking its ack. That's really stupid. We shouldn't do that. Okay, so let's start like writing down problems. We are acking acks. Okay, so then do we drop? How often are we dropping in response now? Weirdly, not a lot. I guess it's because we're double acking so often. Maybe like the dropped packets aren't causing problems. Oh, but it's supposed to be we're dropping incoming packets. Interesting. Interesting. So let's think. I guess I don't want I want to make sure that we're only doing this on TCP frames. And let's just try this again. So we'll netcat, we'll say hi. Okay, so here we're seeing problems for sure. Here our sequence numbers are not right, and so we're rejecting them probably. ACK did not match sequence num. Okay, so let's maybe look at this Wireshark capture and see if there's anything interesting there. Okay, network dump. Here we go. And so did he do anything interesting? He sent a syn. We sent back a syn-ack. He sent an ack that we probably just never received. And interesting. So are we supposed to handle that okay? TCP dropped ack and shake. The syn-ack is retransmitted. I see. So if we don't see an ack, we're supposed to retransmit the syn-ack. That makes sense. Because our only, like... Yeah, that makes sense. Okay, so let's start there. That's a good place to start looking. Which means that we start having to like getting into like retransmission queues. So we can say syn-ack retransmission. And what we can start doing is we can actually like write a test for that should fail. And we can like then test our retransmission queue through a unit test here, which would be kind of fun. So we'll say test dropped ack syn. We'll test a dropped syn-ack. Which means that we need to like initialize our TCP subsystem here. Just struct TCP, I think. Nice. Okay. So we'll say let TCP is equal to TCP new. We create a listener. Is a TCP listen at port, or we'll say 127.0.0.1 at port 9999. We say that our we want to like get a connection, right? So we want to say like connection is equal to listener where are we at? Listener connection dot await. And then what? We want our... I'm trying to think of like, do we actually need this part? I think we do need to store our listener and connection. And then what happens is we want to just start like punching in TCP frames. And eventually we should get a handshake. So I guess in the case of a dropped ACK, what we want to do is we want to make sure that we still get this connection. So let's first start by maybe we take a Wireshark capture of a handshake without any drop packets, and that will give us like the TCP frames that are coming in that we need to do the handshake, and then we can try dropping it and seeing if that, and seeing that we get a syn-ack back. That seems reasonable. Okay. So cargo check, we compile, cargo run, right? We initiate our handshake, boom, and we look at the Wireshark dump. Fuck. Open recent. Network dump. Okay. And what do we see here? Syn-ack, ack, right? This is the part we're looking at. So I guess we will overwrite this syn that we had before with a new one. Oh, we actually can't. Ugh. We'll put this in this test. And down here, we'll say that, how do we do this? Copy as hex stream. Nope. Can we copy as escape string? Sure. That seems reasonable. Okay. This is a constant. Okay. I don't know if these get like automatically concatenated, so we'll just do this. And then our syn-ack is this, and so then we get the ack after. Copy as escaped string. Okay. And here we delete this stuff. And we join all of these into one line. There we go. Okay, so what we should have here is we should have, if we feed this into our TCP system, we should first get a connection. Yeah, so I think I should just say let F1 is the F1 for future one is this. And when we have let F2 is the part where we like feed the TCP system. So we'll say tcp.handle frame, and we'll pass in the TCP syn as the first frame, the TCP ack as the second frame. We need to set the source IP that this came from. So this, okay, let's match this up with the Wireshark. So this came from 192, 168.2.2 was our side. The source is 192.168.1.1, and the source port was 39864. So now we can pass in the source IP and source port here. This. Cargo check. Let's just make sure it compiles. Cargo test, I mean. There's all sorts of stuff it doesn't like in here. So we're missing a bunch of types on here. So let's put some ampersands on these guys. This is these are U8 slices. This guy is a IP adder, and this guy is a U16. We're getting close. These are probably backwards, so handle frame. Source IP. Oh, this isn't source port, this is dest IP. So this should be 192.168.2. I think 2.1. 2.2. That's me. So this is an IP header as well. And here we're listening on the dest IP. This guy wants to be dest IP. This guy wants to be dest IP. Easy. We compile now. Still far. So we need to generate the TCP frame from these guys. So let frame is equal to TCP frame new TCP syn, TCP-ack. Then we pass in the frame like this. Probably with an ampersand. Target test. Are we close? Okay, we are very close. We just need some semicolons. Cargo test. All right. So we have our test now, and now what we want to do is we want to make sure that both of these features run. So we'll run. We actually are in this weird state where this part needs to come first. So we run this here. So we say let listeners this. Then once this is run, it's sane to run this feature here that like does what we need it to. And then what we want to see is that F1 is ready to go. So here we will run F2. And I think we don't actually need these to be in a separate block. We can just say like this. This doesn't even have to be an async block, I guess, which is kind of cool. I thought it did. Hold on. Oh, it does. This needs an 08 on it, I think. Nice, okay. Cargo check. And now we just need to make sure that we run this feature. So we'll say f1.await. For now, this should complete, at least. And we actually see it not finishing ever. So that's an indication that we are not testing this correctly. Is everyone else working though? So where is this hanging is the question. Yes, this is hanging on waiting for the connection. So that's interesting. I would have thought that this connection would initialize. So I wonder why it's not. Let's maybe log what's happening here. So let's start by logging the frames and make sure that everything is as we expect. So the first thing we get is a syn, maybe. Well, let's double check this. So we want the first thing to be this syn, which is a source from 3507H99919. So 3507H9999. Let's print the flags. Flags. Which has, oh, it doesn't, we don't have like a nice debug printer for that, but that's TCP flags 2, which I think just means syn, if I remember correctly. So I think that's fine. Frame 2, it doesn't like actually. So let's make sure that we copied the right thing out of this TCP-ack. So this should be this guy. Copy as an escape string. One sec. And then we join and we merge target test. Okay, so that's better. The second one isn't crashing. So I think that I did just copy the wrong thing before. So we do have our syn and our ack. Syn-ack for non-existent listener is a problem. Why is it printing that? Syn-ack for non-existent listener. Okay, so that means that the listener... Did we get the port wrong? So we are source port, desk port, okay. 9999. So do we have that 9999 locked in correctly? Yes. Is the destination IP wrong? Handle frame, this comes from like source IP, dest IP. So the dest IP should match. That's interesting. Interesting. I guess what we could do is we can just print out what listeners exist and we can compare. So here we have a print line and we can just print out our listeners. I didn't like that at all, which is reasonable. What is this guy? This is a hash map of keys to... Okay, so let's make this debug so we can print the listener key. Keys. Can we just print out the keys like this? So here we have a TCP listener for 192.168.22 port 9999. But he's still saying that there's a syn-ack for a non-existent listener. So what is my key? We're trying to access with this. Oh, okay. So somewhere we've got this backwards. Checking again. So we did. So what's the problem here? Our source IP. Sorry, brain is melting. We're struggling. So here we look at our listener key, which comes from the source IP and the frame desk port. Is that correct? This should be source port, not the desk port, right? Am I crazy? So when I come in, like, how do I look up my listener? No, this should be the desk IP. Because the listener key is, like, me. And so, like, an incoming packet is coming, its destination is me, and so its destination IP should also be me. Okay, so that looks right. Do I still get an error log there? No, that's a good sign. Okay, so we fixed that. Great. And now we are, in fact, getting through these okay, and probably with a successful transmission of a syn and an ack, we probably should end up in a case where our connection occurs. And that's indicating that where it is. Like, the fact that these tests exit at all means that this is working, right? Because if I comment this out and I say, like, hey, we're not going to inform the TCP subsystem of this ack, our connection handshake should never finish, right? And we get stuck here forever. So let's, I guess, instead of running this blocking thing, we can say we should be able to, like, poll this future one time and get a result. So we can say, I think there's future poll function. Poll immediate. Creates a feature that is immediate ready with an option of value. Let's see what these difference between these are. Poll in the, so I guess we look up futures on the Rust docs. And we look at poll function. So That's not useful. That is not useful at all. So let's go back here. Oh god. How do I just get back to like the main page? Here we go. So there should be a future poll function, and what's poll immediate do? Creates a future's immediate ready with an option of value. Specifically, this means that poll always returns poll ready. Ah, this is actually exactly what I want. So I want to poll immediate this guy. And we just want test that it's equal. Not test that it's equal. We just want to say that if it's... We want to make sure that there is something there. So we'll say if let sum, or if this is none. There we go. We will return an error saying connection not ready. Okay, so if we cargo test, this should pass, except I fucked something up. Because we need to await this, actually. Nice, so that passes. And then if I drop this, we shouldn't hang, but we should get to failure. Yeah, we say connection not ready. Sick. Sick, sick, sick. Okay, so we've got our test set up to let us try this, like, failing syn, this, like, dropped syn-ack. And what do we expect to happen now? So if we don't get an ack back, we should expect that TCP service does something, right? Like we send out our syn. Oh, I guess we actually need a TCP service in here first. Hold on, let's see here. Let's see here. So okay, sorry, brain melting. Okay, so we're going to, after we get our first incoming request, we expect that we will generate a syn-ack for that incoming syn. And so we need to make sure that that happens. So if we just call TCP service.await, what happens is we have like a loop running somewhere that pulls sorry, I'm wrong. What I was going to say is that we have a loop somewhere that like pulls the TCP service, and like if it has something to do, we'll like get a packet from it and send it out. But we actually also get that from handling the frame. So here we kind of like expect this response is the syn-ack, and then here we have the ack. So what we want now to happen is without any frames coming in, eventually we have to notice that we didn't get an ack for our syn-ack. And this is how we would handle this, is like every once in a while we'll pull this service and we'll go like, oh shit, it's been too long. We need to resend our syn-ack. And that's going to require some notion of time. And I think that's okay. I think that'll work out. So probably what we do is this service function should take in the time, right? That's the first obvious piece here, because otherwise we won't be able to take the timeout. So we'll take in a clock here that is a monotonic time, but actually we don't need to take in the clock. We can just take in the time itself. So we can just say like time as an F32. Is that reasonable? So then we can check the last time. This will be fed monotonic time, and we can assume it's great. And that way we don't have to like manage a mock monotonic time in our test. Okay. So let's then check that we, in main, pass this down where we need to be. So Here, our TCP service loop needs self monotonic time dot get. Okay. Let's see here real quick. So we actually need this monotonic time to probably feed us back something in a unit that we understand, right? So instead of here, we should probably check our initial time. We know our initial time is 0 because we initialize 0 every time. So we can actually say that like pub function get f32 or get seconds, I guess we can say. And this will return self.tick or self.get over times. What's our tick frequency? Our tick, we're going to have like 4 ticks a second. So we divide by the tick frequency. That seems right. Right, so if we have like 4 ticks a second, we go 0, 1, 2, 3. 3 over tick 3 is 0.75. Great. Sounds good to me. And so here we can say get s. Cargo check. Cool. It's compiling, everyone's happy. And now we can start stubbing out like how we expect our test to behave. So I guess we'll service one time at like 0.1 at like 0 seconds, right? We come in at 0 seconds. And I guess we also have to say when we handle a frame what time that happened at. So this also has 0.0. This guy also needs a time as an F32. Well, we should probably name these time S so that we can remember our units. And in main, we need to pass in the time when we retrieve frames as well. So here we'll just say handle frame monotonic time dot get s. And now we need to propagate this like timer all the way down. So we'll say monotonic time is a monotonic time. And now we just have like a fuck ton of piping to do. So monotonic time goes here. Monotonic time goes here. Like this. And I think we're almost there. Monotonic time goes here as well. Okay. Do we compile? Cargo check. We sure don't. So we go to 397 here. We are missing a propagation of monotonic time down. That's annoying, so we need an async move probably here. And I think that's actually fine. Cargo check. Yep, everything compiles. We're chilling. And so now we can say that we got this frame at time 0. And if we service at time like 5 seconds in, we should expect to receive something. So we can say that we service once. Shit. I was going to say we could service once at 0.1 seconds and be like, nothing to do. Right? Because it hasn't been long enough for anything to have been going wrong yet. And then we could service again at like 2.1 seconds and be like, should resend syn-ack. Now, the problem with that is that this TCP service waits until the time is like at a certain value, which means that we actually might have to punch it out, like pass in the entire clock, or service this every once in a while. Let's think. We want, like here, he would have to schedule a wake up. fuck. That's annoying. So the way that our like executor works is that we have let's pull this open. We have this like future executor, and he only polls basically when an interrupt happens, right? So like he like polls until he gets pending, and that nobody's like requested to wake up. And after that point, he just sits there until an interrupt happens. And the interrupt will like he'll loop every time an interrupt happens, he'll loop through here again. And so the way we have like a sleep implemented is we have this like wake up list that we feed into an interrupt that fires every time the clock changes. And we basically say like, hey, wake up list, wake up our executor if there is a wake up that needs to happen. So that means that there's actually like multiple pieces that we need to like run a sleep. We need to know the time that it is, which is done like in this interrupt increments the time every time it runs. And we also need to keep the list of things that like trigger a wake up. And so the reason I'm talking about all of this is because in our TCP service, if we want this guy to wake up after a certain amount of time has passed, it's complicated because we have to pipe all that data in. But I think that's pretty I think that's like maybe what we can do is we can just hold on to the wake up list here because we know we're going to need it. And maybe what we should do is maybe abstract all of this like wake up logic behind something called like a sleeper, right? We could have like sleeper as a reference to our overall sleeper. And then we could just call like sleeper.sleep or, yeah, sleeper.sleep. I think that's reasonable. Let's think about that just a little bit more, what's going to happen here is I'm going to have like multiple frames come in. We're going to log the time that we sent out our syn-ack, right? And maybe we'll have like 5 syn-acks that we sent out, right? And so the question becomes then like, we need to wake up when any of them are ready to go. So I wonder if there's some way that we should be tracking all of this together as a like, right, I could say that I have like a sleep and I could just take the minimum value and use that as my sleep, whatever. Or we could have a more complex state tracking thing that like supports sleep for the minimum of n values. And I think that I don't want that. I think it's fine to just have a sleeper.sleep. We've explored it. We're ready. Okay. So here, we have all of this, and let's just we already have this like sleep function that takes in monotonic time and he takes the wake up list, and let's just make a sleeper instead. So we'll have struct sleeper, and he takes some things by reference, right? One of them is the monotonic time, and one of them is the wake up list. And then all we have to do is create struct sleep sleeper already exists. Are you crazy? No, it doesn't. No, it doesn't already exist. Oh, it's because I'm calling this from somewhere. Oops. Okay, then our implementation is going to say that we have a function sleep that takes in self and time in seconds. And all this guy does is he uses this sleep feature. All right. Sure. And he takes in these guys. Oops, these are, sorry, this should be self dot. This should be self dot. And then here we say sleeper. Time is monotonic time. No, we'll just do the same thing here. Fuck it. Okay. This needs to be like this. And I think this can be a anonymous lifetime. Okay. So now we have to pass this sleeper down, and we're actually now getting into this case where when we create our TCP subsystem, we actually might want to mock this guy out, which is fucking annoying. Let me think about that. So our unit tests now become like kind of harder because we can't just service at specific times. We have to service with the sleeper in mind. Unless we have like a external loop that handles the sleep and wake up, and we can have like a polled version of it that we call from our unit tests. That seems pretty reasonable. Okay, so in our where is it? In our TCP subsystem, we have this service loop, and he knows the current time when he's called. Really, I guess he should be able to pull the time whatever manually. Thinking. So if we had a like function that's like poll that returns an option outgoing TCP packet, we could then call something. I'm thinking that like this is like the one-shot version, and this is the like wait for something to happen and then do it version. But I think that that's not really trivial with how this is set up. Let's think. This guy is waiting for any of them. Yeah, they kind of just like all happen at once in this version, which kind of sucks. Well, it's kind of nice here, but it sucks for this unit testy implementation. I am thinking again. So maybe let's just start with the non-unit test version and kind of see where that takes us. And then maybe we can like implement a unit test based around that. Does that make sense? No, I'd rather handle it here. Okay. So all of this is leading me to think that he shouldn't be taking in the time as like a one-shot value here. He actually does need the monotonic time in general, which then makes me think that here we pass in the sleeper as well as the monotonic time. Here we have sleeper, and monotonic time. These are now lifetime constrained, like this, which means that this needs an anonymous lifetime like this. This guy needs to take in the time like this. monotonic time, and sleeper, which takes in sleeper and returns TCP. I guess probably we need to tie all these lifetimes together like this. And this takes in time and sleeper. Right. Okay. Consider using the -a lifetime, so this has to be like this. And this needs to have a lifetime here. Okay, we're getting close. What is it bitching about now? Oh, because we already use -a down here, so this just turns into B, I guess. Cool. Cargo check. What's it doesn't like? Yeah, there's some things that it won't like here. The poll function that I stubbed out there doesn't exist, so we'll just smack that guy away. We need to pass in the pieces that we need for this guy. So 242, it said. TCP new, this guy needs a self or monotonic time and a sleeper. Which I guess comes from sleeper. Sure. So we say let sleeper is equal to sleeper new with the monotonic time. And the wake up list. We have the sleep module. We actually need to like export a way to create these things. So we'll say this needs to be a public function here. This needs a public function new that takes in these guys and returns sleeper. Jeez. Okay. This is gonna have a lifetime associated with it now. This is gonna have a lifetime associated with it now, and we're just gonna return this like this. So this gets replaced with a comment, this gets replaced with a comment. I think that all lines up now. We just need to set the lifetime at the implementation. We're close, so this needs to be an and, this needs to be an and. And now we're actually getting into... Oh, is that okay? I thought we were going to have some more lifetime issues here. Almost certainly. So, TCP 324. He's in trouble. TCP RS, so 324. Yeah, we can just pass in A's right here as well. Our TCP lifetime needs to be named now. And actually, this is problematic. So the problem is that the kernel is going to own these he like owns the monotonic time. And if the kernel owns the monotonic time and TCP, then we have like conflicting lifetimes if we try to take this in by reference. So we're just going to solve that for now by using this as like an RC. Just use some shared references, unfortunately, to like help Rust deal with this shit. Does my sleeper need to be the same? It does. This also needs to use RCs. Just to make the types nicer. So I can actually just remove the the A lifetime everywhere. So we'll say substitute this with nothing. And then here we need to take out these angle brackets. Here we need to use alloc RC, the shared pointer type. Oh my god. Please, please. I need this to hurry up. Okay. So I think that's chilling. I think this is chilling. We might need to clone these. No, this needs to be RC here. This also needs to be RC. Cargo check. I'm sure there'll be like a billion compiler errors. Nice. Let's go back into the TCP stuff. Jumping around a little bit, I know, but we're kind of tackling everything as it comes. So we'll delete the lifetimes from this. These now take RC monotonic time and RC sleeper. And this is no longer like this. Okay. It's still looking for some lifetimes because we used B. We changed this name to B, and now we can go back to A. Here. Which actually, that would have bugged for sure. So we're chilling. When we create TCP, we can do RC clone and RC clone. And here we need to make this guy an RC. And please tell me that's all of it. Consider removing the borrow. So here we say RC clone and RC clone. Okay. And we compile again. Thank fucking God. Before we move on, I just want to think about if there is like reference cycles that's going to be a problem. Because like if the kernel owns a sleeper as well as a monotonic time, and the monotonic time stashes the sleeper, I don't know like what happens once we drop everything in the kernel. All references will be cleaned up and it'll be dropped fine. Okay, cool. We're chilling. I don't think there's any like cyclic references or anything like that. Okay. So now our TCP tests are unfortunately just going to be like totally fucked up again. So we need to create a monotonic time. So this is going to be like, Jesus. Use create monotonic time, and we also need the wake up list. And the sleeper, I think. We say this guy takes in the monotonic time of the sleeper. So we say let time is equal to RC new monotonic time new. I think that's all we need. And then the sleeper, the wake up list is RC new wake up list new. Which we could probably just have to import somewhere. So use create. Oh, we already have that. Nice. Monotonic time expected an argument. This is a tick frequency, which we'll just say is like 1.0 or something, 0.1, I don't know. Yeah, we get 10 ticks per second, sure. We'll pretend. We create our sleeper, is also RC new, sleeper new, and he takes in the time and the wake up list. Which are, one of these needs to be cloned. And thank God we are here. Cargo test. Fuck. We were close. I misspelled time. Fuck. Forgot a semicolon. Oh, thank God. Okay, so we're back to this hanging forever. That's interesting. Where is this hanging forever? Let's just quickly comment everything out, figure out where it's hanging. So that doesn't hang. This shouldn't hang. Yeah, we're chilling. This, I assume, shouldn't hang. Oh, we're hanging because we're calling these services in here. Oops. Okay. And there we go. We're back to everything working as expected. Now, since the TCP system now has like time internal, we don't have to pass in the time anymore. We'll mock it out. I think. I don't know. We'll figure it out. So here, this no longer needs to pass in monotonic time. Here, this also no longer needs to pass in monotonic time. And then in our TCP tests, we also don't need to pass in the time. Oh my God. Nor do we here. Test pass again. We compile, we run. Jeez. Okay. Can I interrupt your progress for a bit and ask some questions? I don't know how long ago you said that. I was probably just like hyper-focused, so I apologize. If you are here, you can ask. I'm just doing some boring refactoring. And if you're gone, I apologize for missing you. Okay. So let's think about, now we have time internal, which we needed for the service loop to be able to schedule when it needs to try to resend a TCP syn-ack. And now the question is, how would I test that? No worries, still here. Sick. Ask away. So I guess we have this monotonic time, and we have like an increment on it. We might just want to add like a setter on this, which is only available during testing. So this will take in self, and I guess we'll just say config test. And in this case, we'll just allow it to like override value. So we'll say self.tick.store val with ordering release. I was wondering what your kernel design was. Monolithic or microkernel, exokernel, or what have you. Do you have a specific design goal in mind? Well, right now, we don't have like the concept of a kernel versus user space. So I guess like monolithic might even be too small. Like we kind of are like shoving the whole OS in there right now. I haven't really thought about it too much. The concept of like microkernel is like kind of fun. I like that idea. But I think that probably trying to push that way is not like the fastest way to get out of this what I want. I think like my kind of end goal here was to just explore, I guess. Right? Like, the only thing that I'm really interested in is gaining intuition about operating systems in general, so that like when I write normal code on like a real operating system, I have at least some intuition about what's happening under the hood. So yeah, I don't really have like, I'm not going to say that I've like decided that I'm going to write a monolithic kernel or a microkernel. I don't even like have a plan for user space right now. I do think that when I split out user space, there's a good chance that I would go towards a microkernel, just because I think it's like more correct. But there's probably a reason why that's not true, but I just haven't got there yet. Yeah, so don't know. Okay, so we now have like this way to asynchronously set the time. So we can this is gonna get like a little tricky. So in our test, we are going to execute, or we're gonna like get a syn, we're gonna send our syn-ack, we're gonna know that that's at a specific time, right? That's like going to be at like time 0. And so then we're gonna want to set the time to time 1, which is gonna be like time.tick frequency times 1 second or something. And then when we call service, we should see that we have something to do. That seems reasonable. So here, if we pulled the service function before that, we would get nothing back. That seems reasonable, right? So here we should have what am I doing here? This is TCP service. Here we should get back nothing. So if we get something back, we'll say unexpected service response. Then we set the time to be far into the future, far enough that we expect the service to give us a syn-ack in response. So here we would say syn-ack retransmit missing. Okay, that seems reasonable. And so now what we expect to see is when I run cargo test, oops, this should be as you size, like this. cargo test. So what I expect to see, oh, we were close. We were so close. We have a mistake somewhere in here. This needs to be cloned as well. This time going into the TCP needs to be cloned so that we can use it externally. There we go. Okay. So what we expect to see here is we expect this first poll of the service. This should give us nothing. And then we set the time, and what we want to see is a syn-ack come out. But because we have not implemented the retransmission logic yet, this fails, which makes sense. Yeah, okay, that's cool. That's cool. So now I don't know what the retransmission time is supposed to be. So let's look up TCP again on Wikipedia. Oh, we have it up in here. So timeout-based retransmission. When a sender transmits a segment, it initializes a timer with a conservative estimate of the arrival time of the acknowledgement. The segment is retransmitted if the segment expires, with a new timeout threshold of twice the previous value. Okay, so I guess in this case, at this point in time, there's been no round trip. So we can't guess. So we just have to set an initial random one. Let's just start and we'll say 1 second, right? We will say 1 second. So where is that? In our TCP system, in our service loop, we should say if we haven't sent anything for 1 second, or if we haven't received an ACK for 1 second, we'll retransmit. So the first thing that we would need there, I guess, is one, we need the timeout, but two, we also need to stash the retransmission packets, I guess. So for now, maybe we say ping a server in Australia and New Zealand, you'll be able to see your max realistic round trip times. I'm sure it can get way worse than that, right? That's max for a good connection, but I could probably get worse, but that's okay. I'll deal with that later. I'm not worried about it too much. Okay, so I need a retransmission queue. And I'm not going to think too much about what this is yet. I'm just going to start typing and we'll see what happens. So I guess in here, let's start with a list of packets that we want to resend after some specific timeouts. Right? If I hit a certain time, then it is time. So I guess we could have we want a hash map that goes from time, or a tick, a monotonic time tick, which I guess is a usize, to packet. Right, so we're gonna have some data. And if we pass a specific time, we resend it. Maybe we don't do a hash map here. Maybe we just have a list of them. So we'll say a timeout packet, maybe we'll call it. Timeout frame. And in here we have a timeout, which is a usize. And this is the monotonic tick. And the other thing that we have is the frame, which is going to be a shared reference to a slice of data. Australia is really, really bad in terms of latency. Yeah, that's true. Don't they all have I think they all use 3G, right? Just out in the middle of nowhere. I think that's what I saw when I was there, but I don't really remember. Okay. So then our retransmission queue is just going to be a vector of timeout frames. maybe these should be sorted, right? Like in reality, we're always going to be worried about the next one, not all of them, but we'll deal with that later. You could sort these by timeout even, maybe. But that's okay. And retransmission key will be default. Okay. So when we send a syn-ack, for now, let's just say that we stash this in the retransmission queue. So we'll have our where is he? Here. Listener send connection. No, that's not it. Here we are. So here we generate a TCP frame, and this is the syn-ack, and here we just need to stash this. So I guess we need a mutex around this guy as well, because we're going to be modifying him from a non-owned context, which means that we need to write mutex new in here. And if we come back down here, we have retransmission queue. We lock it, we await, we push. And here we push in a timeout frame. And the timeout is going to be self.time.get plus 1 second times self.time.tick freq. And this is all cast back to usize. And frame is going to be our response frame. So we're all RC clone response frame. Okay, so we're kind of in like a little bit of a pickle here, because our current response frame is a vector, but we need it to be like a shareable, cheap copyable type now. So we're just going to convert this into a RC U8 like this, U8 array. And so now then we're going to start seeing like compiler errors everywhere, and we're just going to have to like bang through them. So I think here we can just type into to generate to convert the vector U8 into an RC U8. Here we need to make this an F32. Cargo check. Here they don't like that this is a option. The response frame, they see it as RC vec or option vec instead of option RC. So here, that's probably just down here. We need a dot into as well. Okay. Oh, that was actually easier than I thought. So nobody else actually cares that he's a vector. Nice. Okay, so now we stash this in the retransmission queue. And if we get this back, we will, if we like receive an ack, we can delete that from the retransmission queue. So that actually gets kind of hairy. We only retransmit if we don't get the ack number. So we actually kind of want to like correlate ack numbers with retransmissions. So here, this retransmission queue actually should be per connection, not global, I think. Because, yeah, that makes sense, because they have to be associated with ACK numbers, and those ACK numbers are per connection. So let's start throwing this in here. So we'll have, for now, we'll just put the timeout in the syn-ack state. Let's think about that, because then we can probably just regenerate it on the fly. No, we'll just store the frame in here. So we'll say the timeout is going to be usize, and the sent frame is going to be a shared reference to a U8 slice, a U8 array, I should say. And now here we don't stick this in the retransmission queue. We put this in the data, like in the state itself. So we'll say sent frame is equal to RC clone and % response frame. And then we're just using the timeout, which is going to be this shit show that I wrote down here. And then here we'll discard these guys. We discard the timeout and the response frame when we receive the ack. Seems reasonable. Okay, we're almost there. We're so close. We're so close. The only thing that we're missing now is the actual retransmission. So in our service loop, here, not only do we check if there's any messages that we want to send, we actually also have to check if there's messages that we have to resend. So we can loop over, this is TCP states outgoing polar. So here we can loop over our TCP states, and we can say if TCP states TCP key, so for key state in TCP states keys, or TCP states, if our state TCP state is syn-ack we then will check the timeout. So this takes in timeout and sent frame. Let's think about that. Yeah, okay, so if otherwise we don't care, so we'll just do that real quick. So if we have a syn-ack send and we pass the timeout, so we say self.time.get if our time is greater than timeout, then we resend the sent frame. So we say outgoing TCP packet. We say outgoing TCP packet, and we need to send the payload with local and remote IP. But unfortunately, we didn't stash that. So sent frame here needs to actually not just be an RCU8, but it needs to be an outgoing TCP packet. Where outgoing TCP packet will now have an RCU8 slice instead of a vector. And here we'll just call into here to fix the compiler. Can you teach me how to code? Unfortunately, I think not. There's a lot that goes into it. You're free to watch and learn and maybe try to gain something from that. But if you're looking for like, I don't know how to code at all and I'm looking for a way to learn that, this is unfortunately not the place, I don't think. What I would suggest is just trying to make something and poking the internet until you can figure out how to do it. Okay, so here we can just return sent frame because now is the right type. We have to clone it. That's fine. Outgoing TCP packet now needs to implement clone. Great. Now probably I have to create this outgoing packet. So sent packet is an outgoing packet with the local IP of dest IP, source IP. Let's see. Remote IP is the destination. Oh shit. This is backwards here too. Let's just patch this up while I'm here. Okay, so in here, the destination IP is where the packet was addressed to, which is me. The remote IP is where the packet came from, which is the source IP. And the payload is our response frame. There we go. And so now in our sent frame is going to be this. So sent frame. And this guy doesn't need to clone anymore. He can just say sent frame. Okay. Do we compile? That'd be cool. We do. Okay, so now we just go back to our service loop. And in our service loop, if we see that we've passed the timeout, we try to send it again. So it's actually possible that this test will just pass now. We might actually get past this syn-ack retransmit missing. Let's take a quick little peek skis. Syn-ack retransmit is still missing. Okay, so that's good. How can we check that? TCP service. So first let's apply this thing that the linter asked for. So we'll say if let this is equal TCP state, just to like make it a little cleaner for our eyeballs. And now I guess what we should do is we should print line self.time.get and the timeout. And we'll see. So this is going to be time and timeout. Okay, so now when we run our tests, we should see why that's not working. So there's actually no log there. That's kind of interesting. And that's because we are not doing anything unless we have a fully connected TCP socket already. And that was intentional because before we were only working with connected TCP sockets, and we didn't want to like hang while we didn't want to like, if there were no connected TCP sockets, something else would break, basically. And so maybe what we do here is we loop over once at the beginning. And here we do this check that we were doing before. Down there. And then we do this poll any connected. And then we should be in a pretty good spot, I think. So let's try that. Let's try that. I'm not certain that this is correct. So down here, we won't run this. And down here, we will pull this back where it was. Okay. So cargo test. And okay, there we go. We're actually getting this listed now, but we're getting time 0, timeout 0. So that's kind of surprising to me. I would think that our timeout should be 1 second, because here we are trying to add 1 second times the tick frequency. And our time should also be non-zero because we incremented it, right? Like here, we set the tick. So there could be like a bug in here. Definitely. And there definitely is. So let me think about this. Here we create a monotonic time, and we actually have this backwards. So we have our tick freak of 0.1, and we actually want this to be like 10. We accidentally did the period instead of the frequency. And now if I do this, hopefully it pulls itself together. So do a 10.0 here, cargo test, and there we go. So we have time at 10, time 20, time at 10. Boom! Okay, that's sick. So we have some more validation to do here. We need to make sure that the syn-ack, we need to like make sure that we actually get a reasonable syn-ack. Is what we got a syn-ack. And I think that's pretty much all we needed. We probably also want to validate that after this we get the connection. But that's probably good enough to fix the test case we had before, like the actual failure that we saw, where sometimes a TCP connection would not succeed if the incorrect packet was dropped. And so let's go back into our main loop, and we can try to look at a drop packet again. So somewhere here, that was here, I think. Here we said, if we dropped 50% of packets, and what we should probably be able to see now is if we run our OS, and we try to connect to it, syn-ack for non-existent listener. That's not good. That's not good at all. Syn-ack for non-existent listener. Where is that coming from? I think that this is actually the bug we were looking at before. Oh, we saw this in our unit test setup, but we didn't see this here. So syn-ack for non-existent listener. Oh, this shouldn't say syn-ack. This should actually say syn-ack. Because, let's see. Because here we expect. Here we've sent a syn-ack. We're not actually expecting anybody to send us a syn-ack ever. We're only ever expecting an ack. So we'll say this is a syn-ack. This is an ack for our syn-ack that we sent out. And so what they're saying here is that we got a... Oh, it's because this should be source IP, I think. TCP listener key? No, this is the test IP. We've got a problem. We've messed this up several times now, where we're messing up like who's sent and who's receiving and what that means. So probably what happened here is we just fucked that up again. So let's print line the listeners and print line the listener key. And run this real quick. So I think this is a netcat, and we run test. And here we have syn-ack for non-existent listener because we are trying to use 2.1, not 2.2. So let's think about that. So destination IP comes from handle frame. Yeah, this is just backwards. That's so fucking annoying. So here the source IP comes first. The dest IP, which is us, comes after. And now I bet that like this is gonna cause all sorts of problems. Fuck. So this is used. Local source, that's correct. Dest source. That makes sense. We are sending a new TCP frame that its destination is the source. That's correct. our outgoing packet, the remote is the source because the source is what came in. Correct. Handle frame source dest. Yup. And here, this just has to be reversed as well. Okay, that's all of them. One more time. Okay, we'll connect, test, and let's see. ACK does not match sequence number. Our sequence number is 76, and their ACK is 47. Okay, so that's at least different. And what we see here is we are seeing some retransmission, I'm pretty sure. So let's run dump network again. And we can look at this in Wireshark. That one is not the one we wanted because it actually worked. We need to roll the dice until we get the dropped packet where we want. Here we go. Solid. So now we kill this, we open it with Wireshark, and we see what the fuck just happened. Okay. So we got a syn. We sent a syn-ack. They sent us an ack. And they are retransmitting their ack over and over again. So this is not the case we were trying to test. We were trying to test the case where we dropped the syn-ack. So let's just give it another run. Oh, I think that actually worked. Holy shit. Oh, fuck, no. I accidentally overwrote the trace. Okay. Okay, so let's see if that was it. Wireshark. Open recent. Network dump. So here, we're looking for a syn-ack retransmission. So they get a syn. We send the syn-ack. They send us... which isn't quite right. We want to see this ack retransmitted. That's what we're looking for. Hey man, awesome work. Are you building it based off Unix or from scratch? Yeah, I guess undetermined as of right now, right? As of right now, we have no user space, which means that there is no concept of Unix. All we have is drivers and a kernel. So you could, for sure, I will be reading stuff. I've definitely read Linux source code. I've definitely worked with Unix. So there's almost certainly going to be some inspiration taken from there. But am I planning on making this a Unix OS? That I guess would be a user space design concept. And I'm nowhere close to user space right now. Although I would probably argue that if I ever want to run real software, I'll need a Unix compatibility layer. It's just guaranteed, right? If you want to have a Python interpreter, it's you need it. If you want to build the Rust compiler, ask Rust to compile for your system, I think that you need it because you need to implement libc, and I think libc is a very at the very least POSIX, right? Maybe Unix is the wrong word, but at the very least you need a POSIX abstraction layer. I'm actually now realizing that I'm confusing Unix and POSIX. So let's double check. What the fuck does Unix even mean? I think Unix might not have a technical definition, and it's just hey, those Bell guys made, or AT&T made Unix at some point, and we kind of copied some design things from there. Standards. Oh, okay, so they made POSIX as a response to Unix. Okay, so then yeah, if I were to try to run real software, I would probably have to make it POSIX compliant. But it's also kind of more fun maybe to not be POSIX compliant. I kind of like the idea of if this goes on long enough, right? It would be fun to for any project that I work on to have to write it from scratch. That's kind of funny. And is kind of in the spirit of what we're trying to accomplish here. So maybe, I don't know, we'll see. Haha, so you actually built the kernel from scratch. Yeah, that's what we're at right now, is all we have is a kernel. So we have a kernel that does these things that's shown in the top right. And we're working on TCP. And what's kind of exciting is once we finish TCP, we're at the point now where we can actually start making something. You could make a web server that runs straight over the kernel, and all of a sudden you can now start doing interesting things with that. So anyways, that's where we're at. What were we doing? We were trying to test syn-ack retransmission. So we want to make sure that we drop a syn-ack. So I guess what we should do here is just if we get a syn-ack, we will drop it manually. That's like, instead of like trying to roll these dice and just hope that we accidentally drop the right frame, let's just we'll say if we'll give ourselves like a 90% probability of dropping the frame. And so we'll say if TCP frame dot flags dot syn and TCP flags dot, or I guess TCP, if this is an ACK, it's not trivial, because it depends on our like TCP state. If TCP dot, gross. Okay, we'll just do it in the TCP service here. So how can we get in here? We have this like handle frame, and we can say if flags, we just want to drop the first one here. So I guess, can we just make like a static int that we can't increment once just for like the purposes of testing? That seems doable. So here we just add a count is an atomic U size of 0 or something. This is going to require an import of like core sync atomic U size. Here we can say that the count is initialized to atomic U size new 0. Here we're going to increment the count once. So I think there's like an fetch add 1 with core sync ordering, or atomic ordering, yeah. Under atomic ordering relaxed. We'll look at the previous value, and then we'll say if this is 1, if prev count is 0, I guess, we'll return. So this is like our like pseudo way of saying like, I'm just gonna like fail to process this incoming packet, and we'll hope that we see sane behavior in response. So this will be return none. Cargo run. So what I want to see now is if I run this, we should see a syn-ack retransmission in Wireshark. File, open recent. And instead, we are still getting the ACK back. That's interesting. Oh, but that's because, so that makes sense. We get a syn, we send a syn-ack, we get an ACK back, and what we should see is eventually a syn-ack retransmission. But we are not seeing that, so let's take a look at that. So let's just look at this. We'll see, we should see ourselves print there one time, probably. Yep. And we don't see that multiple times, which is good. And I guess here we want to see here in our service loop, I want to see that we hit this timeout. Right? So let's... shit. Okay, so the problem here is that what happens on the first iteration here, we loop through our like possible syn-ack, like our possible outgoing syn-acks, and then there are none, right? We're gonna get to the point where we say like, okay, nothing to handle. And then we're going to come down here and we're going to say like, now we're going to wait for any connected. And so what we actually just have to do here is this like poll any connected is like not what we want. We're waiting for any connected or any unresolved syn-acks that need to be resolved. So putting this up here like this was fucking stupid. What we should do is put this down here. And this poll any connected should be poll any connected or syn-ack timeout, which means that we should do this loop in there where we are looking for any syn-acks that have been timed out. So here this is now guard instead of TCP states. We can do this in the TCP key. We can like do this in the same loops where we're looking for connected. So this is like this now. Here, this if statement gets converted into a match, like this. And if the time is greater than the timeout, we return that we're ready. And I think that's it. And now we just need to inject the time in here. So we have time is, I think it was a monotonic clock. And we need the timeout. So the timeout's here. Perfect. Cannot mutate immutable variable. We don't need it to be mutable. Okay, so we're chilling. And now all we need to do here is when we create this like polar that's going to wait for something interesting to happen, one of the things that we're going to pass in here is the time, which is a self.monotonic time, self.time, I think. Yeah, like that. Wow, is that actually it? That'd be sick. That would be sick. Cargo run. Okay, so we're going to try to connect. We're going to say test. And did we get something interesting in there? Let's look at the Wireshark capture again. Fuck! I was really hoping to see the double syn-ack. So what am I missing? What am I missing? Because as far as like I'm concerned, this should work. So I guess what we can do here is we can I'm thinking. Fuck. I found it. Okay. So we were talking about this earlier. A lot of this piping that we were doing during this stream was to get this like sleep guy in here. Now the problem is that like our future runtime, it will only ever wake up when an interrupt fires and it tells us to wake up. And so we need to register a like wake up time with this. And this guy will like, what's gonna happen is he's gonna like come in the first time and he's gonna say like, yeah, we didn't receive an ack, and so I need to wait for like end time. But we have not like scheduled the sleep. So I think that actually what we want to do is instead of passing in this sleeper, we can take in like we can just register a wake up time, which is an RC wake up list. And here, instead of taking a sleeper, we've taken a wake up list, which is like basically the way that we register with the interrupt handler. We like punch numbers into this wake up list, and then the interrupt handler like he gets like a time, and he goes like, is it time to wake up? Let me look at the list, and he finds someone in the list. He goes like, sure fucking is time to wake up. So that's what we're changing to here. Instead of like asking for explicit sleep, we'll just register our time with the interrupt handler. Which means that somewhere here, when we inject our timeout, we actually need to register with the wake up list. So here, so we'll say let timeout is equal to this. This shit show of a string here. I think it's all of this. We'll say self. Oops, I have an extra curly brace here. So this is now timeout, and we say self.wakeuplist register wake up time, and it's at timeout. Okay. We're chilling, I think. And now we just have to make sure that in main we like construct this with the right stuff. So here our TCP sub module needs to be constructed with the wake up list. And we don't need the sleeper anymore. Cargo check. A cargo run. Sick. Okay. So we connect, we say test. And I guess what we should do is somewhere we should just print if we're trying to send our retransmission. Instead of like manually checking Wireshark every time. So here, no, not here. Here, we will print line. Oh, we do print here that we're trying. So in here, I don't think we ever got that like log, which indicates that this poll any connection never finished. So let's say print line hold for sure. Cargo run. God, this is also complex. So here we got that pulled thing. Ah, fuck. I bet it's this. I bet it's this. So I'm just gonna quickly log here, just so for my own understanding. Yeah, okay. So what happened is we're in the same state again where we had some assumptions about what we were going to be doing before that we're like not matching now. So here we are correctly waiting for if it's time to send something. But here we come down and we like construct this like list of futures. And we say like, for each of these futures, I'm gonna wait for if I request to send some data to the other side. But down here, then we like wait, and we never try to send any data, so we never notice that we have to do a retransmission. So what we need to do is what? What do we need to do? I actually can't. I'm actually not sure. So here, it's probably something about the fact that we're just immediately breaking out of this loop here, when really maybe it's like this outgoing polar for this guy. Yeah, he needs to resolve if the timeout is time. Yeah. Okay, so in here before, we were only waiting. We were saying like, hey, if we receive some data, that's when we're ready. But now we can also say, if we're in this state here, and we're in this state here, we are ready. Yeah, that seems reasonable. And there's a bunch of stuff that doesn't like here, so let's start figuring that out. Match arms have incompatible types. Because oh, I see. So basically we need to say like, if it's a syn-ack sent, this is not right. But if it is if it's a syn-ack sent, we've got nothing to do. Unless the timeout is wrong. So let's look at we need to inject the time here as a monotonic time. And then here we have time is self.time. All right, this has got to be the one. This has got to be the one, baby. So here we'll run netcat, we'll run test. And no, still no? Oh, I guess I didn't have the log. I deleted the log, actually. So how can we test that? I guess here we'll print line, it's time. It's time. And maybe here, we print line it's not time. There we go. So here we connect again, we retest, and do we see either it's time or it's not time? No. That's interesting. Are we seeing polls happen? So let's see if we're polling this at all. So here's a test, and we are seeing a bunch of polls. And I wonder if we can say which key we're polling. So we'll say TCP key. Oh, it doesn't like that. This needs to be self.tcp key. Come on, man. TCP key's not loggable. Come on. So this is debug. Okay. So here I connect. I write some test. I'm polling this guy a bunch of times. But we're never seeing the syn-ack state. Can I log what state it's in? So here in my outgoing polar. Did I post the whole process somewhere you're interested? Yeah, definitely. If you look in the Twitch description, there's a YouTube link. And in there, I'll have all the videos posted in a playlist called Writing My Own OS, I think. And if you want to look at the code itself, we have that up as well here. I'll post that in chat. All right. Come on. Let's think a little bit. So here I have this outgoing polar. I'm trying to understand why I'm not seeing myself in the syn-ack state. Right, so I wanted to print which state I'm in, which means here I'll say print line connected, and here I'll print line syn-ack sent. So it's possible that I'm like transitioning between states too early. And let's see. Yeah, so the problem is that like I'm in this connected state, and I should never be fucking making it there, because I send my syn-ack and I shouldn't be getting an ack back. So let's look at the Wireshark again, and we'll try on dump network, and I'll try to understand why the fuck I'm seeing this like movement between states that I'm not expecting. So we're gonna test here, bing bang boom. We are connected like almost immediately. Okay, and let's take a look at that. So we open the recent network dump, and here is a syn-ack. Oh, and maybe it's because we send this like test string, and it thinks that that's the ack that it's looking for. So we can actually maybe test this by saying, in our TCP state machine, if I get if flags.push, push, we'll pretend that we didn't get it, just temporarily, in this state. So here we can say test. Oh, baby. That's good. Okay. So I think that we're very, very close there. So here we're seeing these logs for like its time. And now the only thing left to do is make sure that we are actually advancing out of the state. So the problem is now that we're not advancing out of the state like we should. But I bet here we need to adjust the timeout is why, right? So if we're above the timeout, we need to bump the timeout again. So we say timeout plus equals self.time.tick freak times 1.0. And here this needs to be like a ref mute probably. And then here we need this to be like a mute connection probably. And this needs to have a star on it. cannot add a sign F32 to usize, so this needs to be as usize. And this doesn't have to have that mute on it like I thought it did. Okay, cargo run. And we're going to try to run a test. Did it happen? Did it work? Oh, that'd be so sick. Boom! Let's go. So here we re-push the syn. We do see this like syn-ack retransmission, which is fucking sick. Okay, so now the only question is am I rejecting too many acks? So here I think I said like somewhere I was only supposed to reject the first one. So let's log print line rejecting ack. Why are we crashing now all of a sudden? What the fuck? Hello? Why is this crashing all of a sudden? This seems like I didn't change anything. That's odd. Is there anywhere in here that could give me a clue? Handle frame, static IP, blah, 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 blah. Trying to subtract with overflow. So somewhere. Timeout is time.get plus. Did I do time.get minus or something somewhere? No, that's plus again. That's so odd. What could I have possibly changed just now that would cause an attempt to subtract with overflow? You take a similar tone with Russ as I do. It's the only way, man. You have to fight him. You gotta yell at him, and he yells at you, and that's why it's a love-hate relationship. That's very odd. I can't think of why I would now be attempting to subtract with overflow. And I don't have back traces either. God, that's so annoying. Okay, let's checkpoint. Right? We're gonna just double check now that it's something I did today. Checkpoint. And if it's not, it's time for a breakaway. Yeah, okay. If I get checkout master. Yeah, okay. Something got fucked probably with the RTC driver. Because it's the only thing that makes sense, right? It's the only thing that's changing with time. So is there like a subtraction anywhere related to RTC time? I guess here I can just return date time. Oh boy, we'll derive default here. And here we'll just return date time default. And let's just see where this is called. This is just like the only thing that makes sense to me. The only thing that makes sense. Oh, and it actually does make sense because in my demo... Oh, hold on. I've got an easier way to test this. In my demo, I try to subtract the hour. And if I'm at hour 0, I bet it just breaks. Yeah, God fucking damn it. Alright. That makes sense. So we'll just do plus equals 1 here or something. Get stash. Right, so the problem was that in my demo, I try to take an hour off of the current time and write it back. Just to prove that we can modify the time. Except that by doing that, I'm actually like taking an invalid time if I'm like at 0 UTC. Okay, so that's an easy fix. So let's go back here. We comment this out temporarily. And we try to see, we go back now to try to test if our like syn-ack retransmission is working as expected. And I don't remember where we were. we were trying to figure out if we're transitioning out of the syn-ack state at the wrong time. So I think I was adding some logging in the TCP system. And I think that I was trying to check here. Print line rejecting ack. And I guess we just do this in a couple places. Cargo run. And so I say nc 192.168.2.2.999. Hi. And so I actually rejected a couple. Rejected again. And can I print line if I didn't reject it? So here, I should say accepted act. So test. And I think I'm rejecting all of his acts. And I never accepted it. Yeah. Okay. Well, I'm hungry and I've been streaming for a lot longer than I meant to. But this is pretty exciting. I think that even though we didn't get to the point where we're handling like network drops correctly, we did get to the point where we could prove to ourselves by looking at our Wireshark captures that we are at least attempting a syn-ack retransmission on drop of act. So that's already like progress. And we actually got to do like a few fun things like in the process on the way there today. We did like implement a like really shitty RNG as a way to try to randomly create network traffic problems. We ended up randomly dropping incoming packets. We did some syn-ack retransmission, and we also did like a histogram implementation at some point. So I think that's like we accomplished a lot today, even though if we didn't hit our goal. And so yeah, if you enjoyed what you watched, you can always tune back in on Twitch live most days at like 2 Pacific time. And if you missed stuff on Twitch, there's YouTube linked in the description, and I'll be posting all of my VODs there as I go. There's source code available on GitHub under StreamOS with the same username. And yeah, and if you're watching on YouTube and you want to catch me on Twitch at some point, feel free to stop by. Twitch link is in the description. Yeah, thanks for watching. Catch you guys on the next one. Bye!